Okay, perfect. So, uh, hello everyone. Welcome to another meeting of our reading group. Today we have another great speaker. As always, if you have any question, feel free to unmute yourself, ask the question from the speaker directly, or you could write your question in the chat. Today we have Titouan Parcollet, a research scientist at the Samsung AI Center in Cambridge and affiliated lecturer at the University of Cambridge. Without any further ado, the stage is all yours.
Right. Thank you, Pune. Thank you for the introduction. Thank you for the invitation as well. It's been a while since I've given a talk, so that's good practice. That's great. So thanks. So let me share very quickly. Share. Oh, this should be good, right?
Yeah.
Good. Okay. Okay. Well, yes. So this talk will be about our work. So that's a work from the speech team at the Samsung AI Center, Cambridge, as you mentioned. And this is the work that we have done last year and at the beginning of this year as well. So the talk will be split in two, basically. But the topic revolves around the same goal, that is speech recognition. And so we'll talk about unsupervised on-device adaptation of a speech recognizer, as well as problems that we have now evaluating SpeechLLM for speech recognition. So, okay, good. So speech recognition, right? It's a broad task. Let's say let's start like this. It's a very broad task, and of course, at Samsung, we're interested in speech recognition. If you just think of Bixby or any smart appliance that we can make in this company, basically there is speech recognition involved, and this can happen both in the cloud or on device. And this is great because it comes with challenges and opportunities that are very specific potentially to each modality where you will apply your speech recognizer. This is exactly why we have two topics today, because we need basically to investigate different things or different problems and try to solve them depending on what we're trying to do. So the first thing will indeed be unsupervised on-device adaptation of a speech recognizer. So that's for on-device speech recognition. And the pitfalls of SpeechLLM evaluation is more for now, of course, for now, as a solution for cloud-based speech recognition, let's say. Okay, so let's jump directly into the first topic. So when it comes to on-device speech recognition, this comes with very big challenges, I'd say, but also great opportunities. So of course there is the hardware constraint. That's obvious. You cannot run at 300 million parameters or train at 300 million parameters on your device if it's like low end or something like this. You need to limit the number of parameters that you're training on device, for instance, but also memory wise, also latency wise. I mean, you have a lot of constraint linked to on device training. But with this comes also real life data, because you are very, very close in that case to the user, right? When someone is talking to Bixby, when someone is talking to a smart TV, whatever, they're actually giving real data so that you are actually dealing with the real task and the real acoustic environment and the real speaker that will talk to your system. So that's great. But the problem is like usually the data that you get is also limited in terms of amount, because people don't talk for hours to their TVs, right? Or don't talk 2 hours, 4 hours to Bixby, for instance. And of course, it might be potentially noisy because you can be on the street or well, it can also be in your cozy apartment if you're talking to the TVs, but you can have quite a lot of noise. And obviously, the last thing is you don't have any labels, right? This has to be unlabeled because well, when people talk to their assistant, they don't then transcribe what they just said. So you don't have any labels, you just have the speech. And so because of this, what we want to try basically as a task when we think of on-device speech recognition, right? The first thing that comes to our mind is personalization, which means we will want our speech recognizer to become better as people are using it, right? So the more one of your user will be interacting with a speech recognizer, the more the speech recognizer should be accurate, right? You want it to improve over time. And so that's fairly simple to picture when it comes to what should be happening. Basically, you have the speech recognizer, right? And you would talk to it. So you would just say something new. And the idea is that everything you've said before should be used to improve the recognition of the current sentence, right? And given what we've said as challenges as well, you need to keep in mind that it has to be unsupervised adaptation, right? So you have to adapt to previous speech. So let's say something done less than 5 minutes, but it has to be done in an unsupervised manner because we don't have labels from the users. So if you want to do this, so this unsupervised adaptation for your speech recognizer, the first thing you want to do potentially is have a look at the literature and understand how people have been doing this, because we are not the only one having to deal with this problem, obviously. So the first thing that have been done, right, is to just do full fine-tuning. So that's the most naive thing that you can think of, maybe. But in that case, the adaptation type would be supervised, right? So even if we don't have labels, we can try some weakly supervised approach that we'll talk about later. The speaker representation in this case is learned, right? Because you are fine-tuning the model to the speaker. And then the number of parameters that you have to train in that case is usually, well, I mean, it's from a few millions to infinity. It depends on the size of your speech recognizer, which is not great for a device. And in that case, the adaptation loss is the maximum conditional likelihood most of the time. So we're talking about the literature, what people have been doing, right? It's not this talk necessarily. We won't talk more about full fine-tuning because in practice it's not good, right? When you don't have a lot of data, you end up with overfitting and it's just too intense for the resources on device. That was just the first thing we can try and do. The second thing that is much more used is to use LoRa, right? So low rank adaptation of your speech recognizer. In that case, the adaptation type from the literature, again, usually it's supervised or weakly supervised, and we'll see later again what this means. In that case, the speaker representation is also learned because you are training your LoRa parameters to adapt to your speaker. And the number of parameters can range from a few thousand, let's say, to more than 1 million, so a few millions parameters, depending on the size of your original model. Again, if you look at the literature, most of the time, people are using the maximum conditional likelihood to optimize with LoRa. What we propose to do, basically, is on the left here, is to use speaker codes and or minimum entropy training. So and or, it's because you can use both, basically. So speaker code and minimum entropy, or not, if you don't want to use minimum entropy. So what it means is that the adaptation type that we will be doing here will move from supervised to unsupervised, but we can also do supervised, but our interest, of course, isn't supervised. The speaker representation is also learned, but this time it is learned with much, much fewer parameters. You can see that we are using only 1024 parameters because this corresponds to a code or one vector. So for each speaker we will have one vector, or again, a code that will be of size 1024. So that's very few parameters, and we only adapt this parameters, nothing more. And the adaptation loss here can be either the traditional maximum conditional likelihood, like LoRa, like standard adaptation, let's say, or minimum entropy that we will talk later about. That is also something we propose here for unsupervised adaptation. Okay, so one thing I'd like to mention here is that speaker codes are not new. They have been proposed for DNN HMM speech recognizers, and we are just revisiting them for modern speech recognizers and adapting them to our setting, unsupervised adaptation, and modern ASR as well. Okay, so first step, when we think about using speaker codes to do, so let's focus on the speaker code part and not talk about minimum entropy for now. If we want to use speaker codes to adapt our speech recognizer, the first thing we have to think about is like, what kind of ASR architecture can we use with speaker codes? Well, the answer is any. Whatever the encoder, whatever the decoder, can be transducer, transformer, CTC, we don't care. Speaker code can be adapted to, can be put in any kind of ASR architecture. So in the context of this presentation, we are using an encoder-decoder architecture. So it's like encoder plus CTC attention. So let's say an encoder that is a conformer and a decoder that will be a standard transformer. But we don't really care about the decoder because the speaker code is only impacting the speech encoder, not the decoder part, because what we want to adapt is for now, is the acoustic conditions, acoustic environment, and variability of the speaker. So how do we put our speaker code into the conformer encoder? So that's fairly simple again, even I would say straightforward. So on the right side, you have your conformer block, typical conformer block. And as I said, the decoder, we don't care, but it's a standard transformer. So what we do is, for each speaker, we have a speaker code. So let's say your speaker code is just an embedding, right? It's like a vector of 1024. We project this vector into with a linear projection, so just a linear projection, and then we add this to the input right before self-attention in the conformer encoder. You can see that we do this after the residual connection, and that's because we want also to allow the model to bypass this corruption. It's not a corruption, it's actually a bias. It's a positive bias that we give to self-attention based on the speaker. And so you can just repeat this in a certain number of blocks. So in our case, it's from block 0 to 5 in the speech encoder. So not all the blocks, half of them. This is based on empirical analysis. And that's it, basically. That's how you use speaker codes to adapt, let's say, to speech recognition, adapt your speech recognizer, sorry. So the way you train this now is also fairly simple. There are 2 steps. The first one is standard ASR training. The only difference that we have compared to another ASR training is that you need to know the speaker ID in this case, right? Because remember, I said one speaker code equal one speaker. And the way this train is that each time we build a batch, let's say, of audio files, if in this batch we have 10 different speakers, then we will give 10 different speaker codes. So one speaker equal one speaker code. And we need the ID to do this mapping. The way it works is very simple, right? Like if you have a speaker, you will train the speech recognizer with the real label. So this is supervised training, right? Like the standard ASR training with a lot of data. And so you will just backpropagate through the ASR system back to the speaker codes. So you will adapt the speaker code to this sample, let's say, or this sample of samples. So this means that the speaker code at the end of this training will capture the whole space of speaker variability. That's not just the speaker ID, but that's also the way the speaker speaks, the noises around, the type of microphones, all this kind of things, right? So if you're always talking in front of your TV in the same environment, this will be very well captured, for instance, by the speaker code. Once this is done, well, you have then a speaker-dependent speech recognizer, basically. But the thing is, when you deploy this model, you are not deploying the speaker code, right? Like you are not in your training set, you don't have samples that come from actual customers or users. So what you want to do is then to adapt the speech recognizer to the new users that will be using your product. And this is where unsupervised on-device adaptation comes from. So in this step, what we do is we deploy the speech recognizer, right? The weight of the speech recognizer on device, let's say, and we freeze it. We entirely freeze the ASR system. The only thing that is unfrozen is the speaker code. So we will just create for each user one new speaker code that will be initialized to 0. And we will adapt it using backpropagation. So you will backpropagate from the hypothesis that has been generated through the speech recognizer that is not adapted back to the speaker code that will be changed slowly as the user talks more to the speech recognizer. So it will be slowly improving towards a better and better speaker code capturing the speaker variability space. So here, clearly, you can see that the hypothesis in this case is a very weak point, right? Because hypothesis is something that has been predicted by the speech recognizer. It might be wrong, and we don't have labels, right? So we need a way to get around this, to send good signal when using backpropagation to our speaker code for adaptation. And that's why we need to jump to the second part of this unsupervised adaptation work, where we need to define new loss or use a new loss to do unsupervised adaptation. Okay, so the motivation behind using minimum entropy is that unsupervised learning is a big problem for discriminative models, right? And unfortunately, our ASR system is a discriminated model. So what people usually do in the literature is that they run the ASR system to obtain pseudo labels, and then they just adapt to this pseudo label, right? So you could do this in the previous step, for instance, just generate some labels out of the samples, and then you just try to adapt to this output distribution. What we propose to do instead is to minimize the conditional entropy. So at a high level, the way you can think of this is to try and make the adaptation more robust to errors in the initial hypothesis. So we somehow use exploration. So we use multiple hypotheses to make it more robust rather than using only one. So you have the equation right here, and we will just jump into it very slowly so we understand what's happening. So Q theta here is just our speech recognizer. And what we will try to do is for each utterance that we have in the dataset, so we sum over each utterance in the dataset. Maybe you can also think of it as like your mini batch, for instance. But in this case, each utterance in the dataset, we will try to, well, it's not we try, we compute a sum over all possible word sequences, right? Given this x being this utterance in the dataset. So the problem, of course, is that this is intractable in practice because we have a lot of potential word sequences for a given input audio or sample, for instance. So what we do instead is to use an n best sequence instead. So we will sum over the 5 best, let's say, predicted word sequences of our speech recognizer. Can be 5, can be 10, you decide, of course, here. And that's it. That's minimum entropy training in this case. So if we want to have a quick example of what it means, what will happen if we train with this. So let's say we have our 4 time steps here. So we have x1, x2, x3, x4. They are represented by 2 variables, as you can see. And let's say that x1 and x2 have the same label, and x3, x4 have a different label, but the same one as well. So if we train a small model to predict for each x and the probability of being a given word in the vocabulary that, as you can see, contain 4 words, you will obtain this little matrix, squared matrix in the middle. And so you can see that it's almost a diagonal, right, in terms of predictions. So what most of the literature would do is just take an argmax of this, and you will obtain the left square, really diagonal in this case, pseudo labels. And with these pseudo labels, we will just adapt the model to predict and to predict even more these pseudo labels, right? So you end up having at the end what you have at the bottom left, so the adapted to pseudo labels probability space. And so basically what happens is like it's wrong because, as we've said, x1 and x2 are one label and x3, x4 are another label. It is wrong, and the model has just learned to be more wrong, basically. While if you minimize the entropy, you obtain what we see at the bottom right. And this is just because of the exploration, right? Because we are taking all hypotheses and into account and not only one. And so we will adapt and obtain this in the end, which is the correct answer. So we make it more robust by using multiple hypotheses, basically. Okay, so what happens then in practice, right? When you try to use this and do something with it, something that is supposed to be useful and working. So the first problem is that if we want to benchmark this against typical solution, we have to use datasets that are available to everyone. And that's hard because we need a dataset with enough transcribed hours, but also speaker IDs for each of the sample. And we also want enough speakers because, well, that's the whole point of our thing, is that we should try with a broad amount of speakers to see what happens. And we want them to have different acoustic conditions and different acoustic environments, which makes it even harder. And we want these acoustic conditions, of course, to be challenging such that it reflects the real life, potentially deployment scenario. So what we ended up doing is building our own data set from Common Voice. And so we just took Common Voice, we corrupted it with Musan noises and music, and we also added reverberation by rendering this in a virtual room. So I've listened to some of these samples. It's very hard, and you will see the water rate later that it's like actually very hard. So this goes down to 8 150 hours of training material. That's not a lot, and the reason for this is because each speaker that we have selected has at least 10 minutes of available speech. This is also because we wanted, basically, you will see later, to vary the amount of available hours per speaker to see basically what is the impact of the availability of data for the water rate. So we end up having a bit more than 1,300 speakers for the training part. And then we have a held out set of 100 speakers for the adaptation part. There is no intersection between these two sets. So speakers in the training set are not seen in the adaptation set. And that's it. And we just started training our model that is given here. So it's 100 million parameters conformer CTC attention model from SpeechBrain, typical recipe. We didn't do anything specific from this. For the adaptation part, we have first, so let's say that's the baseline, LoRa. And so if you apply LoRa to this model, you obtain 1.6 million parameters that will be fine-tuned outside of the 100 million parameters that are not fine-tuned. And of course, the speaker codes, as I said, so you have 1,024 parameters to adapt to the model. And in that case, we added them from layer 0 to 5. It's the same speaker code applied to the 5 layers. One thing I should mention that I think is very important is that during the speech recognition training, so that's the first phase where we do supervised training, right? The speaker codes are dropped half of the time. And the reason for this, when I say dropped, is like set to 0. And the reason for this is very simple. And when you have done your training, if you don't do this and you deploy your system to new users on device, the speaker code for these users, they don't exist, right? They are zeros. And so if you haven't made your speech recognizer robust to this case, where speaker codes are 0, of course, the water rate will be terrible. And this is exactly what you want to avoid, because that's where you want to grab the user somehow. Like if the first interaction they have with their speech recognizer is terrible, they will not talk enough for the speaker code to become good, and so the speech recognizer to improve, because they will just not use the service at all. So doing this makes the model robust, such that when you deploy the system, it's just performing, even without adaptation, just as well as the model that has not seen any speaker code at all, which is what we want, of course. For the adaptation, what happens is that we fine-tune, so we adapt the model on a per speaker basis. So we have this 100 speakers, and we adapt to each of them independently. So we start from the speaker dependent model, but an adapted model every time for each speaker. And then we average the water rate that we obtain for the speaker. Okay, so let's jump into the results. So in that case, we have only 1 minute of data, right? So 1 minute of available unlabeled data per speaker. So across the set of 100 speaker. So the first thing we see, top line, is our baseline, right? So that's the speaker independent system. That's what would have happened if you train a speaker independent, so without any speaker code during the ASR training. So normal ASR system trained on the 850 hours. And then you just compute the water rate on the test set of the 100 speakers, you obtain 24.4 water rate, which is super high in terms of like production water rate. That's terrible. So this means that our task is actually very hard, which is good, because this is what we want to have. Then the second thing we can see on this figure is that whatever the adaptation method we use, so you can see that we have 3 blocks. We have LoRa, we have speaker codes, and then we have speaker code plus LoRa. And below this, we have the different losses. You can see that whatever the method of adaptation, minimum entropy is always outperforming pseudo-label loss, right? So whether it is speaker code LoRa or speaker code plus LoRa, it's always better to use minimum entropy because of what we've seen earlier, right? And it's even more visible with LoRa. Again, that's because LoRa has more parameters, so potentially more overfitting problems. And so if you use pseudo-label loss, it will increase overfitting because of what we've seen. You're just making the model more wrong when it's wrong. The second thing we can say is that if we look at the best result that we have achieved, so that's speaker code plus LoRa, so we just add everything here, basically. So we just add the speaker code and LoRa on top of this, and then we do the adaptation. You can see that we see a 20% relative improvement of water rate. And this is with only 1 minute of unlabeled speech. Just to remind everyone, this is with 1 minute of unlabeled speech. So I think that's pretty good, actually. So you may wonder then, what if we have more available speech per speaker? Well, simple story as well. So that's a graph showing this. On the x-axis, you have the minutes of adaptation data available per speaker. On the left, you have the water rate that has been achieved. So the first thing you can say is that if you look between 0 and 1 minutes of adaptation data, you will see that with this amount of data, so it's not a lot, but actually realistic, you can see that speaker code plus LoRa are actually much better, or speaker codes are also better than LoRa. LoRa is terrible, which is again normal because of overfitting, as we can think of LoRa. Then as the amount of data increases, then it might become better to switch to LoRa if you are using minimum entropy. If you're not using minimum entropy, this is like the bar at the top, so the label loss, you can see that LoRa is terrible, again, because of overfitting due to the pseudo label loss plus the number of parameters of LoRa. But overall, if you use minimum entropy loss, switching to LoRa makes sense if your amount of data increases, and minimum entropy, as we can see here again, is always better to pseudo-label adaptation. So then you might wonder, okay, but maybe these improvements are actually supported by only a few speakers and the others are not improving across the set of 100 speakers that we have. So what's the distribution of improvement here? So this is exactly what is displayed here as well. So you have the actual speakers on the x-axis and the water rate reduction between an adapted model and adapted model after adaptation. So that's a water rate reduction. So you can see that most speakers are improving, right? And if you look at the bottom graph, you can see that speaker code plus LoRa is the one giving the more consistent result. Like the curve is slightly smoother than the others in terms of improvement. And most of the speakers are improving. Whatever happens, only a few are degrading, very few. And we see the most improvement with the speakers that have the highest water rate at the beginning. So this is not shown here, but this is what we've seen. So higher the water rate, the better the adaptation improvement we see. Okay, so to conclude this first part, basically, I just want to give a few advice, basically. So if you don't have labels, right, do not use adaptation with pseudo labels. Do not use pseudo labels, right? Use minimum entropy training. It has been clearly shown here. It's massively better, always better, because it's more robust, right? Then if you have very few samples per speaker, which is quite common in realistic condition, then you should use a combination of speaker code and LoRa. And you can switch to LoRa, of course, if you have like a lot of data. And again, the headline here I would like to really showcase is that we have done adaptation of a speech recognizer that can be on device. And we obtained 20% of improvement in terms of water rate compared to the adapted model with only 1 minute of no label, like unlabeled speech at all. So I think that's pretty good. But that's also time to jump into our second topic, which is the pitfalls of speech LLM evaluation. Right. So why do we even care about speech LLM when it comes to speech recognition? I think it's quite clear to everyone that the connection between speech plus LLM has attracted quite a lot of interest in the past few years. If you look at titles only of interspeech paper linked to language models, I mean, the growth is clear that there are more and more people interested into this topic. And we've seen in the recent month and even years for the first ones, a lot of new models that enable us to interact with LLMs via speech directly. So with that in mind, we could wonder, can we use a speech LLM to do ASR? Yes, we can. So then we need to think about how to evaluate them. Why? Because, well, it's just completely wrong the way we do it right now. So that's the introduction of this part of the talk is we start with the conclusion. LLMs that we are using in speech LLMs, they are trained on test set of speech recognition benchmarks. That's just facts. So then, if we know this, so if we know that there is this bias, this contamination, we need to know how bad it is in terms of proportion. And of course, it is actually problematic. If it is actually problematic for speech recognition, if it will impact the model benchmarking that we usually do as a scientific community. So for the first question, how bad is the contamination, we can just have a simple use case and look at LibreSpeech, which shouldn't be used for speech recognition evaluation anymore, by the way, because it's too simple, too small. But still, a lot of people are using it, at least for, let's say, prototyping. So LibreSpeech comes from audiobooks. It's very clean, but it's like an ensemble of speech text pair for speech recognition, very common for speech recognition. It comes from the project Gutenberg. Unfortunately for us, the pile, for instance, the dataset, the pile that is used in most LLM pre-training also come from Project Gutenberg. And we can see from the first Llama 1 training data description that they were also scrapping the Project Gutenberg to train the models. And most obviously, Project Gutenberg is like a massive amount of resources to do text stuff. So most LLMs will rely on it. So if we just look at the pile now and we try to see how bad the contamination is with respect to LibreSpeech, we can do some fuzzy text matching. So try to find LibreSpeech test and validation sentences in the pile. If we do this, we can see that 60% of LibreSpeech validation and test sentences are in the pile, right? So your typical LLMs have been trained on at least 60% of the validation and test of LibreSpeech. So that's roughly 7,000 sentences out of 11,000 sentences. And you can apply this to most speech recognition data set that we are using. You can do this with Common Voice as well, and you will discover that a third of Common Voice, this depends on the version of Common Voice, you keep updating it, but at least a third of Common Voice validation and test set are also in the train set of the pile. So knowing this, like the contamination is clear and it's big. So because of this, we are now in need to see if the actual evaluation is affected and if there are bias here. So it's actually hard to verify. So we just tried to build a very simple test just to give us at least some insight about this problem. So what we did is train a bunch of LLMs, all above 1 billion parameters, from scratch and on part of the pile. And what we did is like have a set of uncontaminated LLMs and a set of contaminated LLMs. So the uncontaminated one, basically, they are trained on 30 billion tokens, for instance, and they would exclude sentences from the dev and test set of LibreSpeech completely. While the contaminated one would have tests and dev and test sentences from LibreSpeech, and let's call them leaked sentences from them. So what we want to see now is the contaminated model more likely to generate leaked sentences, basically, right, than the uncontaminated one? So that's the question. How likely is each model to predict leaked and non-leaked sentences? So to capture this, we have to look at the word level negative log likelihood predicted from the output of each model. So this is like an average across all word in the evaluation set that we are considering. So LibreSpeech, dev and test sentences. And so in this case here, we only have two models, right? So 7 billion parameters each. One is contaminated, bottom row, while the other one is not, top row. And if we have a look at the leaked sentences first, so that's on the right, lower is better, we can see that the contaminated model is more likely to generate leaked test sentences. It is actually more likely. And if we put this in context with the non-leaked sentences, so it means that none of the two models have actually seen this sentences during training, you can see that then there is no difference between these two. So between these two models on non-leaked sentences, which clearly indicate that leaked sentences for the contaminated models are a problem. They are more likely to be generated by the contaminated model. And so you may wonder, then what's the difference? Because we have like plenty of LLMs, right? So what happens if you increase the size of the model? What happens if you increase the training size? So you reduce basically the amount of contamination with respect to the training material. So we did this, right? And so we looked at the differences in log likelihood between contaminated and uncontaminated LLMs. So it means that, so that's what we show in this graph. But basically, what you see here is the, sorry, the difference in log likelihood between contaminated and uncontaminated LLMs. So which means that if you are in a negative like this, well, in that case here, the contaminated model is more likely to generate these sentences, right? And so you can see that whatever the number of parameters, whatever the number of tokens, the contaminated models are always more likely to generate leaked sentences than the uncontaminated one. There is a problem here, clearly, that we are more likely to generate these sentences. Right. But then maybe we don't care when we go to speech recognition, right? Maybe this doesn't matter because this was just LLM. There is no speech involved. So what happens when you condition the LLM on speech embeddings? So the way we do this, very simple. We don't go on crazy architecture. We have a pre-trained speech encoder, Wave LLM. We have a pre-trained large language model, the ones that we've trained before, so contaminated and uncontaminated, and we connect them by just training a small projector, and that's the only things that we train. So it's like 2 dense layer, let's say, in the middle. That's the only thing that is being fine-tuned, right? And we fine-tune this projector on LibreSpeech, 960 hours. So the speech encoder and LLMs are frozen, so we don't have any more bias, basically. Okay, so first we look at the log likelihood again. And same story than what we've seen earlier, basically. So you can see that the contaminated speech LLM, so the one using the LLM that has been contaminated, is more likely to generate leaked sentences than non-leaked sentences. It's statistically significantly better on leaked sentences when prompt with speech embeddings. So that's on the LibreSpeech test claim, by the way. Okay, but what we care. Okay, well, one extra step. Because of the LLM, we can do punctuated ASR as well. And you can see in this case that it's actually even worse in the case of punctuated speech recognition, because you can see that on non-leaked sentences, it's unclear if there is a difference between the two models. But on leaked sentences, again, it is very clear that the contaminated model is more likely to predict the sentences again. What happens when you go to speech recognition? Because this is like loss, right? We don't care about this and when we look at the transcriptions in theory. So let's move to actual water rate. Well, there is no difference anymore. That's the plot twist of the story, is that when we look at water rate in this setup, right? So that's LibreSpeech test scheme, and it's with a reduced set of speech LLM, and it's very specific. But in that case, the water rate it's unclear, right? So we can see that the contaminated model has always better water rate than the non-contaminated one. And there is a lot of variation in the end in the different training runs that we've done. That's just because there is a lot of variability, and we cannot tell because of this variability if it is statistically significant or not. So we cannot see when it comes to water rate an actual difference. But let's put this aside and conclude. Here, what I would like to really stress is that the evaluation protocol that we have for speech recognition with SpeechLLM is scientifically invalid. This is invalid, right? Because we have a very significant test set contamination of LLMs. So scientifically, there is a problem here. So then when we look at what happens because of this, well, we can see that contaminated speech LLM, they only differ very subtly in water rate, and it's unclear if there is an actual problem with water rate. But it is extremely clear that the likelihood of generating leaked sentences, so the contamination, are very much higher than uncontaminated models. There is contamination; it's visible from there. And so if we put, even if just we put the impact aside, so this numbers aside, I really would like us to get back to not train our models on test set, please. So if you are involved in this line of research, be very wary of this, or at least acknowledge this kind of limitations in your work, because this is really a new thing, let's say, because we never did this in the past for speech recognition, or it was deemed to be completely invalid in the paper if you did this in the past, right? And not only speech recognition. So it should still be the same now, I think. That's my conclusion, basically. So thank you very much. And if you have questions, well, I'm done.
Thank you, Titouan, for the talk. If you guys have any questions, please drop them in the chat or raise your hand so you can ask them directly to Titouan. So someone asked, did you try to measure performance of speech LLMs on a new dataset never seen by the LLMs before? And did you notice a performance degradation that you wouldn't see with the classic ASR model?
No, we did not try this. I'm not sure if it, because like, so we would have like performance things, but I'm not sure that this would give us insight on the impact of contamination, right? Because what we're, or maybe I did not understand properly the question. Let me reread this very briefly. Did you notice performance relation that you wouldn't see with a classic ASR model? Oh, okay. So I'm not sure if I understand this correctly. Well, yes, you can see different errors from a speech LLM compared to an ASR1 because speech LLM they don't hallucinate, but they are wordy. So they produce transcriptions that may be more wordy than the actual ASR system, for instance.
Okay, thank you. Mirko, do you have a question?
Probably could not hear you if you're talking or something.
Yeah.
Maybe meanwhile I could ask my question maybe. Thank you again for the talk. It is like very interesting. One question that I have regarding your final conclusion that we should not use the test set when you're working with this speech LLMs, but it is a little bit hard to see what they used it when they training these language models. So like what is the best practice that you suggest? So how we could know what they use? Is it a need for coming up with new data set or like what should we do here?
We can't know because they don't publish the data, right? That's the famous open source thing. So what we can do is to try and at least avoid data sets, so speech data set that are, well, the problem is like they are scrapping the whole the web, so it's hard, but we can try to limit this at least by using data set that may not be as obviously contaminated than Libre Speech and Common Voice, for instance, because Common Voice is Wikipedia. Of course, they are using Wikipedia. Libre Speech is a good Project Gutenberg, but we could think maybe of data set that are a bit less like this. Like for instance, I don't know if we start using Shime data set or things like this that have been used in the context of created in the context of challenges and things like this that might be much smaller, obviously, but still, it would be better to use them because it's less likely that they have been using the transcription of this kind of data set to train the LLMs because they are much smaller, right? But as soon as you start touching things that are linked to YouTube or things that are very easily accessible on the web and creating a lot of text, there is contamination.
Makes sense. Thank you.
Hello?
Yeah.
All
Yeah,
right.
I can
Yes.
hear you now.
Finally. Good. So yeah, actually my question was similar to that, like asked by Pune. In general, what can we do, right? So because this is a problem bigger than just speech audio. It's actually involving really the way we assess the performance of LM, right? In general, because the contamination is everywhere. So I'm wondering, what do you think about maybe creating some kind of like evaluation only data sets which are like accessible in a kind of blind way where you just like submit something, you get the results, but we don't have the actual transcription, something like that. Yeah.
Well, I mean, that sounds great, but then you need someone to do it.
Yeah, of course. Not saying I'm gonna do that. And just thinking about what could be a solution for that, like to make sure that your evaluation is not contaminated.
Right. So to me, the best solution here is like if you have enough. So there are a few LLMs that are not as powerful as Llama and not as powerful as the big out there, but that are still fairly good. For instance, we use Pythia LLMs for which you can control. They actually disclose what the training data is. Or you could even train, well, okay, that's somehow a bit, it costs a bit of money to do this, but you can train your own LLMs on the pile, for instance, and they would still perform well. Like if your line of research is just trying to make the best speech LLM in a precise task like ASR, for instance, then you don't really care about using the best LLM because you want to assess what is the best architecture. So as long as the comparison is fair, you can use an LLM that you know the data is the pile only, for instance, or data set that has been described properly. But I agree with you, like ideally we want some sort of data set that is hidden somewhere that they cannot access.
Yeah,
but it's also a lot of resources to do this.
sure. Okay, thank you.
Thank you. Artem asked, has anyone run or considered a Kaggle competition? They use this approach where they hide the test set.
I have no idea.
Okay.
Maybe. I mean, for companies, it can be easier because then they usually have some held out private data. But for academics, it's a real problem. It is a real problem, I think. Yeah, and my advice would just be use LLMs that are not as good as the best ones, but at least you can see what the data is, exactly what the data is. But of course, if you are like doing some sort of speech plus LLM in a conversational setup, you want the ones that are the best at discussing with humans, and then you need the big ones. But still.
So
I'm reading.
there's like yeah, maybe
Yeah,
you could just is it okay if you could read it loud, because then
oh sure.
Yeah, thank you.
So there was one mention about going back to testing on Hub 5 eval dataset switchboard, which is licensed under LDC. Well, we successfully went out of license dataset, I think, and potentially SpeechLLMs are forcing us to get back to this as well. But maybe they also pay to train on it, so I don't know. And so the long question is, to be more precise with my previous question, if you create a brand new speech dataset, you can be certain the SpeechLLMs have not been trained on them. Then you measure the performance on this dataset of a SpeechLLM and a classic ASR model. Let's say SpeechLLM makes 10% less on uncontaminated benchmark. Then if contamination specifically improves the performance, we should notice that the SpeechLLM advantage decreases or even disappears. What do you think of this protocol? Yes, but you need to do a new speech dataset first, and this is costly. This is very costly, actually, and also because you need to do a speech dataset whose material that you are using to generate the speech. So you ask someone to read it, or I don't know the way you do this, but you need the material to not be something obtained from the web, right? Otherwise, you're screwed again. Because the LLM will have seen it. Because in the end, LLMs have seen everything, right? So the only thing that we're left maybe is like human conversations, like trying to transcribe meetings or this kind of things, where this protocol would make sense in that case. Yeah.
Maybe I have one more question from the first part of the talk. So how do you get the speaker information that you set in your training data? Do you use any speaker identification model and use the embedding layer? Like where the information come from?
For Common Voice, you have the ID you have the ID information, right? So it's not perfect because unfortunately the ID is just it's a cookie ID, right? So if someone has recorded on different devices, so with different cookies, you would have the same speaker with different IDs, potentially. but that's fine. That's a risk okay to take. So what we did to make sure there is no contamination, however, with the held out set of speakers, we actually use a SpeechBrain speaker verification system to make sure that there was no match between the speaker of the 100 set and the full training. But you need the actual labels. So you need the labeled data set. You could maybe just do some supervised clustering or something like this if you don't have it, of course. But also, I mean, like if you don't have this and so you still want to do adaptation, you can use minimum entropy, because minimum entropy works for speaker dependent and speaker independent models. So like if you use LoRa and no speaker code, you can still train with minimum entropy, and so the initial model will just be a model that hasn't seen any. It's speaker independent basically. So you don't need speaker ID in this case if you don't have them.
So in the supervised phase, all the speaker IDs are initialized with 0, and then it trained the embedding from scratch. Oh, I see. Okay, makes sense.
Well, so we've tried initializing with speaker vectors, let's say. It's performed worst, basically, which makes sense to me because speaker vectors have not been trained with ASR in mind, right? While the speaker codes are optimized for ASR, so they will capture speaker information for ASR.
I see. Okay, perfect. Thank you. I think Mirko has another question.
Yeah. Do you try to see what happened, like if you inject the wrong speaker code, right? So just to see if that is destroying the performance or still acceptable.
Yeah, well, I mean that was one of the use cases, of course, that you need to check for production, because it is most likely that someone may be using your phone and your Bixby.
Right.
And so there is a degradation. So I don't have the graphs here. There is a degradation, but it's not going from impossible to recognize what you're saying. So you would maybe say, I don't remember the numbers exactly. Maybe Titouan can write them on the chat if he remembers, but I think it should be around like 5% water, right, or something like this. So there is a degradation, but it's not breaking the system, basically.
Yeah, I think for a phone makes sense because typically, right, it's personal. But for the television, it's a little bit different because the television, many people might use the television. I don't know, my wife, myself, my kids. So in that case, maybe I don't know, there should be some kind of, I don't know, speaker identification or something like that. Yeah.
Yeah. You should have, if you have a camera, maybe you can identify someone, or if you don't have camera, then speaker ID before doing the ASR.
Right. Makes sense. Thank you.
Okay, last call for the final round of questions. Someone said, I remember degradation is quite small compared to the word error rate of the unadapted model. Okay.
Yeah, which is good, which means like it's still better in the end.
Okay, perfect. Thanks a lot for the presentation, for the talk. Next week, we have Oriol Nieto from Adobe Research, and he's going to talk about Gen AI for sound design. Looking forward to meeting all of you next week. Thank you all.
Bye. Thanks.
Bye.